Okay, section 10.2, the gas laws. So now what we're going to do is we're going to look at some mathematical relationships between the physical properties of gases. So the first one we're going to look at is called Boyles Law. And this is what we would call a pressure volume relationship. Okay, pressure and volume, or PV. All right, so the idea here is that if you take a gas and put it in a cylinder with a piston, the atmosphere pushes down on it. So there's a pressure downward, but the gas pushes up. So the gas is in the container here. The gas pushes up on the piston as well. And what will happen is eventually there will be some equilibrium. The piston, or the piston will stop moving and it'll be stable, quasi-stable anyways, when the two pressures are equal to each other. Now the question then is, what happens if we apply more pressure on the outside? So we push with even more force down on the piston. Essentially what will happen is the piston will move down. So it'll move down. I'm just going to show it all the way down to there, right? Okay. So this is called compression. This is where the gas is now occupying a smaller volume than it originally did. It's in here. So what that tells us then is that the pressure increases, the volume decreases. So how do we write that mathematically? One way is to write it as what's called a proportionality. Remember, a proportionality tells you whether something goes up or goes down, but it doesn't tell you the actual amount. So we're going to write it this way. 1 over v. This is sometimes called an inverse proportionality, meaning that if one variable increases, the other one decreases. So in this case, if the pressure increases, the volume decreases, and vice versa. If the pressure decreases, the volume will increase. Okay? So now, how do we deal with this equation? How do we use it? Well, I'm going to rearrange it. I'm going to multiply both sides by v. So now I have P times V is proportional to 1 over V times V, or just 1, right? So the pressure times the volume is proportional to 1. So what that tells us is 1 is a number, right? And mathematically we call, or in the sciences, we call a number a constant. 1 is 1, it doesn't change. So what that tells us is that the pressure times the volume, P times V, is equal to a constant. Okay? And that's called Boyles Law. Okay? So there are many different permutations of the equation here. I'm going to show you a couple of them. One is V is equal to K, K meaning constant, times 1 over P. That's one way of representing it. Another way of representing it is P times V is equal to K, K being a constant. Okay? Another aspect of this is that if the pressure of a gas times its volume is a constant, that means that this situation here, okay, the pressure of the gas here times its volume is equal to a constant. So we'll call this case 1. Now suppose I compress the gas. So now it's occupying a smaller volume. We'll call this case 2. All right, situation 2. Well, it's also true here, right? If the pressure times the volume is a constant, it doesn't matter what the pressure is or the volume, the product of the two is a constant. So let's call this P1, the initial pressure, times V1, the initial volume, is equal to K. Well, that's got to be this case over here. P2, the pressure under this case, times its volume, that's also got to be equal to K. So that means that P1 times V1 is equal to P2 times V2. So that's another way of expressing this Boyles relationship, or this Boyles law, which says that the pressure times the volume is a constant. That's very useful for solving problems. But we should point out one thing. There's one thing that implicit in all of this is that it's at constant temperature. If it is not at constant temperature, this all falls apart, and we have to use a different law. But if it's a constant temperature during this whole process, we would call this Boyles Law. Okay? So that's the first relationship. Of course, there are many different problems you can solve on these, and you can look at the sample problems and the practice problems and all of that. The second situation that we want to look at is the relationship between temperature and volume. And there are two names to this law. The first is Charles' law, or Charles's law. And the second one is called Gay-Lussac. Okay, same name for the same, or different name for the same relationship. And this is what we would call a volume-temperature relationship. Or relation, okay? How the volume of a gas is affected by the temperature of the gas. Now, there's very nice little demos and things you can see on the internet where you take a balloon and you pour liquid nitrogen. Liquid nitrogen is at a very low temperature, and then what happens is the balloon shrivels up into a tiny little thing. So that means that if it gets really, really cold, the volume goes down. Okay? So that's generally true. Essentially what happens is the volume of a gas is directly proportional to its temperature. Okay? Now, just like with Boyles' law, there's a certain assumption here, and for this case, the assumption is that the pressure is constant. And if that's not the case, then we have to deal with that separately. So, that's one way to write this relationship. Another one is to make it an equation, V equals K times T. That's one way to represent it. Another way to represent it is to divide both sides by T and get a K. So the ratio of the volume to the temperature is a constant. Or just like with Boyles' law, this balloon has a volume and a temperature, and it still has a volume here. It's much smaller at a lower temperature, right? V1 over T1 is equal to a constant, but that constant is also equal to V2 over T2. So in other words, V1 over T1 is equal to V2 over T2. So here's another way of relating this, or showing this relationship. Okay, notice there's a bunch of them, right? This one's pretty useful. It's probably the most useful of all of these that are listed in here. Okay, so now let me make a little point here in discussing this, and that is the issue of temperature. We have stayed away from talking too much about temperature so far, but I want to talk a little bit about temperature scales. There are three scales that you've perhaps heard of. So I'm going to draw three little scales here. The first one is called Fahrenheit. Now, I almost don't even want to talk about Fahrenheit because it's not a scale that we use in chemistry, but it is one that people are most familiar with because our temperature is generally given in Fahrenheit. The temperature of Fahrenheit is based on certain relationships. So one relationship or one fact is that water freezes at 32 degrees Fahrenheit, right? So that's where water freezes. And then water boils. Do you know what the answer to that question is? What temperature does water boil at in Fahrenheit? 212. Okay. So, what's another temperature we might be familiar with? We might be familiar with the temperature of someone, the human body, right? The human body is at a temperature with about 98, 99 degrees. 98.6 sometimes people refer to it. And then what's the lowest possible temperature? It's around 459.67. This is the lowest possible temperature. Okay, lowest possible temperature, negative 459.67. Now there's another scale called the Celsius scale. Okay, and when we're talking about water boiling, that happens at 100 degrees Celsius. By the way, the little symbols we use, degree F for Fahrenheit, degrees C for Celsius. What's the human body temperature? Well, it's around 37. And water freezes at 0 degrees C. Okay. So the nice thing about the Celsius scale is that its 0 and 100 points are based on water. Okay. And what's the lowest possible temperature on the Celsius scale? Negative 273.15. Okay, so the low end of the temperature scale is negative 273.15. So notice with Fahrenheit and with Celsius, you can have negative values. Okay. You can also have 0, right? So water freezes at 0 degrees Celsius. 0 degrees Fahrenheit is a very, very cold day, but certainly possible. The third scale is the one that's most important for us in this chapter, and that's called the Kelvin scale. K for Kelvin. And under the Kelvin scale, it is essentially shifted up so that compared to the Celsius scale, the lowest possible temperature is 0. I'm not going to put a little degree sign there for the Kelvin scale. We don't use the symbol degree. So under the Kelvin scale, the lowest possible temperature is 0, meaning there are no negative values possible. If we shift it up by that amount, then 0 degrees C would become 273.15. And 37 would be what? 310.15. And then 100 would become 373.15. Okay? So the conversions are degrees Celsius is equal to 5/9 times degrees Fahrenheit. 5/9 times degrees Fahrenheit minus 32 degrees. And then degrees Celsius here. Oh, let's do it this way. Degrees Kelvin. Not degrees Kelvin. There is no degree sign with Kelvin. It's just Kelvin. So Kelvin is degrees C plus 273.50. And I'm going to circle this one because this is the one we're going to use with gas laws. Anytime we do calculations with gas laws, we want to use the Kelvin scale. And the reason for that is that at a molecular level and at an energetic level, negative temperatures make no sense. And 0 temperature, although it makes sense, is essentially never possible. We want to use a scale that has only positive values. And so for that reason, the Celsius scale and the Fahrenheit scale are not used in gas law problems. Okay, so anytime you see a problem that has a degree C in it, convert that to Kelvin by using this relationship right there. Add 273.15 to the temperature in Celsius. I'm going to put a little asterisk there to remind you that this is an important point when you do these problems. You do not want to have the temperature in Celsius when you do these problems. Okay? So the third relationship that we want to talk about is called Avogadro's relation, or Avogadro's law. See if I can delete all this. Not too bad. Okay. So we'll call it Avogadro's law. And this is volume moles relationship. Or relation. Okay? So this essentially says that if you put more gas into a container, and the container can inflate or increase in size, it will. The more gas you put into a balloon, the bigger the balloon gets, right? So we want to think about this in terms of a balloon. The more gas that you have in a balloon, the bigger it gets. Okay, so one way of writing this mathematically is that volume is proportional to moles of the gas. Now, it would also be proportional to the mass, but for various reasons, it's more convenient for us to use moles as the unit. And so I'm going to use the symbol N for moles. So N is the symbol we're going to use for moles of gas. Just like the other two relations, Boyles Law, Charles's Law, or Gay-Lussac, the assumption here is that the temperature and the pressure are constant. If they are not, if either of them or both of them are not constant, then Avogadro's law fails and we have to use a more sophisticated relation. Okay? So we can write this equation in different ways. We could say V is equal to a constant times N. Or we could say V divided by N is equal to a constant. Or we could say V1 over N1 is equal to V2 over N2. As we've seen, that's a possible way to relate it. This is maybe the most common way to relate this. What it says is, in this balloon over here, the volume of the gas, the volume of the balloon, divided by the number of moles of the gas in the balloon, is going to be equal to the volume of that balloon, how big that balloon is, divided by the number of moles of the gas in there. Okay? So that is Avogadro's law. The next relation essentially takes all of these and puts them together. Oops. So if we take them all and put them all together, so let's remind ourselves, Boyles Law, PV, Charles's Law, VT, Avogadro's Law, VN. We can combine them into what's called combined gas law. And the combined gas law is very useful. What it says is that the pressure times the volume divided by the number of moles divided by the temperature is constant. So I'm going to write it this way. That ratio, that monster of a ratio, is a constant. Okay, so if we change the pressure, volume, temperature, and moles, we can still predict what's going to happen using this relationship here. I will point out that very often the number of moles is constant. For many problems that we work on, the number of moles is essentially constant. So it simplifies to this. P1 V1 over T1 is equal to P2 V2 over T2. Okay. So that is an alternate form of the combined gas law if the number of moles of gas is constant. You're more likely to see this relationship than you are the first one. Okay? These are fun problems to work on. They're easy, they're proportionalities, they're really neat. So practice as many of these as you can, and you'll be an expert on these laws, on these gas laws.